Um, okay, so there's a horizontal beam that's connected to the wall at its right end. And then it makes a 45, 45, 90 triangle. It's a vertical beam that's at the midpoint. And then there's another beam that, I have to change this connection. So this is a roller. And then at the midpoint of the vertical member, there's another beam that connects to that corner point. This distance is 1 meter. This is 1 meter. That means this is 1 meter because those angles are 45 degrees. And there's an external force of 5,000 newtons. It makes a 30-degree angle horizontal. I'm going to neglect all the weight. And we want to know what are the external loads on each of these members. Okay, so the first step is I'm going to number all these members so we can refer to them. I'll call the horizontal one 1, and then 2, 3, 4. And I'll name the joints too, so I'll call the wall A, the other pin on the horizontal member B, and then C is the roller, D, and E going up. All right, so what's the first step? The two-step process for doing structures. What's the first one about? Oh, we just did that. Okay, I'm thinking of dynamics. Okay, what's the next step? I don't know how many numbers there are then in my set of steps. That's right. Okay, so let's think about what's happening at each of these joints. A is pretty simple. C is pretty simple. D is pretty simple, but let's think about what happens at B and E. And I'm going to do that by drawing like side views of these. So all of these side views of the joints are like what this gentleman sees. Okay. That's a mustache. Okay, so the joint B. He sees member 1 over on the right. Then it looks like member 2 in the middle, and then member 3 on the left, and a pin going all the way through these. So this one is member 1, member 2, and member 3. And of those, which one of these members is the pin associated with? 1. So we'll treat that all like it's one thing. And so based on that, what members are touching member 1? 2 and 3. What members are touching member 2? Just 1 and member 3? Just 1. Yep. And then at E, there is member 4 on the right, and then member 2 on the left. And a pin going through them. And then there's also the 5,000 Newton force applied to the pin. What member is the pin associated with? 2. So this is a single thing. So what loads are acting on member 2? Yeah, so there's a force F24, and then also the 5,000 Newton force is applied to member 2. And what loads are applied to member 4? Only 2. That 5,000 doesn't show up for 4. Okay, what's another step? I really have no idea what the step is. I have a vague sense of how to do the problem. I don't want to, I don't want to make you nervous about that. But yeah, I don't remember what steps I told you. Okay. Yes. Correct. So first, free body diagram of member 1. It wasn't that great. All right. So member 1. Right end, there's a point. So that means there's a force vector. I'll call that RA. And then a couple MR, reaction moment. And then there's a force at the midpoint applied by the vertical member, member 4. What does that force look like? That's right. That's a pushing contact or a roller joint. So that force is perpendicular to the surface of contact and toward the chosen member. Any questions about that one? So I'll call that, what letter is that? RC. And I don't put a vector symbol over this because that's a scalar variable. We know the direction of that one. And then at the left end point, that's joint B. So if we look at this side view, we have a force F12 and a force F13. So 1, 2, 1, 3. Any questions about the free body diagram? Okay, so now we'll set up the cable, calculate the row vector, force vector, and the moment. Where do you want to choose as the about point? Yeah, that'd be fine. I think I'm going to choose the left side because we have 2 unknown force vectors there, and that means that in the moment equation, neither of those 2 are going to show up, but you can put it wherever you want. So for these 2 forces, the row vector is 0. Force vector is F12x, F12y. Cross product is 0. Then for F13, the row vector is 0. Force vector is F13x, F13y. Moment is 0. And now the force RC, the row vector from the about point to where RC is applied is, that distance is 1. So that's positive 1, 0. The force vector, that's in the negative y direction, so that's 0, negative RC. And the cross product is negative RC. And then the force RA, the vector from the about point to where RA is applied is 2 in the positive x direction, 0. Force vector is RA, x and y. And the cross product is 2RAY. And then the last load is that reaction couple, MR. We don't care about any of this stuff for a couple, so I'll just write this in as MR. Any questions about those? So Newton's second law will add up all of the forces, set them equal to 0. We have F12 x and y plus F13 x and y plus 0, negative RC plus RAX, RAY is equal to 0s. And then the moment equation says negative RC plus 2 RAY plus MR is equal to 0. Okay, so our first three equations, we have the x equation from Newton's second law, F12x plus F13x plus RAX is equal to 0. The second one says F12y plus F13y minus RC plus RAY is equal to 0. And then the third equation says negative RC plus 2 RAY plus MR is equal to 0. All right, so we have three equations and variables. We have F12 x and y, F13 x and y, RC, and RA x and y, and MR. A lot. We have a lot of variables, way more than 3. So the variables are the vector F12, the vector F13, the vector RA, and then scalars RC and MR. So to count those up, we have 2, 4, 6, 7, 8. Any questions about that? So now let's go to member 2. That's the diagonal one, the higher diagonal one. Down at the joint B, what loads are acting on member 2? So look at this side view. That's right. So all there is a force on 2 by 1, which in order to have the minimum number of variables possible, we'll just call that negative F12. And then up at the other end, at E, what are the loads applied to member 2? Yeah, F24 and then that 5,000 Newton force. So F24 and then this one. Let's see. I think I'll put the about point up here. So first, I'll deal with F24. The row vector is 0 for that. Mm-hmm. Okay, so the idea here is, so if you look at, this is where that force that, you're talking about that 5,000 Newton force, right? So that 5,000 Newton force is applied to this pin. And so this is the side view of that pin. And you can see here that if we treat the pin like it's part of member 2, that 5,000 isn't applied to 4 at all. It's only applied to 2. And so that's why in the free body diagram for 2, it's going to show up. But when we isolate 4, it's not going to be there. It does affect the reaction force, but that's not what we're asking ourselves. We're just asking what loads are directly applied to each member. Okay, so up here is the force F24, X and Y components. Moment is 0. And then for the 5,000 Newton force, the row vector is 0 again. This angle is 30 degrees below the horizontal. So that's cosine and sine of negative 30 times 5,000, which is 0.433, 4330 when you multiply. And then negative 2,500. And the moment's 0 for that. And then for the force negative F12, we need the vector that goes from the about point to where F12 is applied. This beam makes an angle of 45 degrees with the horizontal. So you can think of that as cosine and sine of 225. And so the length of that, we don't even have to actually think about it that way. We know that this distance is 1 meter, and we know that this distance is 1 meter. So that row vector is just going to be -1, -1. And then the force vector is negative F12x, negative F12y. And so the cross product is positive F12y minus F12x. So Newton's second law says F24x, F24y plus 4330 negative 2500 plus negative f12x negative f12y is equal to zeros. And then the moment equation says negative f12x plus f12y is equal to 0. So these three equations are numbers 4, 5, and 6. Equation 4 says f24x minus f12x is equal to negative 4330. Equation 5 says f24y minus f12y is equal to 2500. And then equation 6 says negative f12x plus f12y is equal to 0. Okay, so now we have 6 total equations. And let's figure out how many variables we have. The ones we had before were f12, f13, RA, and then the scalars RC and MR. We still have those, so f12 vector, f13 vector, RA, and then the scalars are, what was it, RC? Yeah. And MR. And now equations 4, 5, and 6 added some new variables. So now we also have the variable f24, and that's a vector. That's the only new variable. Yep. Mm-hmm.
So whatever you write it down is so yeah, the f12y minus f12x.
Oh, I just switched the order. I don't know. I'm just used to putting the x1 in front of the y1 in the equation. So now for variables, we have 2, 4, 6, 8, 9, 10. So we're starting to catch up. 6 equations, 10 variables. Any other questions about that body? And now member 3. So that's the other diagonal member, the middle one. At the pin B, what loads are applied to member 3? Yep, so it's the force on 3 by 1, and that's negative F13. What was that? Negative F13. And then at the joint D, what loads are applied to member 3? Force on 3 by 4.
Can you remind me again whenever you have a force on one?
Yes, it's on the first one by the second one. So one way to think about that, let me write this one down first. So F3, 4. So the body that you isolate only has loads on it with itself as the first subscript. Okay, so if you're isolating member 3, all of these should have a first subscript of 3, you know. And then we substituted F31 for negative F13. But that's a way to sort of remember that that first subscript refers to the body that you're isolating. And that's everything on that one, right? So, yeah. Okay, so row moment. The about point down here. For the force negative F13, the row vector is 0. Vector is negative F13 x and y. Moment is 0. And then for the force that's at that point B, the row vector, so we're talking about the vector that's going from B to B. This is at the midpoint of the vertical member. So horizontally, in the positive x direction, you go 1 meter. In positive y direction, you go half a meter. The row is 1 positive 0.5. The force is F34x, F34y. And the cross product is F34y minus 0.5 F34x. So Newton's second law says negative F13x, negative F13y, plus F34x, F34y is equal to zeros. And the moment equation says negative 0.5 F34x plus F34y is equal to 0. So we have 6 equations so far. Now these are 7 through 9. Equation 7 says negative F13x plus F34x is equal to 0. Eight says negative F13y plus F34y is equal to 0. And 9 says negative 0.5 F34x plus F34y is equal to 0. We have 9 equations, and the variables are 1, 2, 1, 3, 2, 4, RA, and then RC and MR. So the variables are F12, F13, F24, RA. RA is a vector 2. And then the scalars RC, MR. And then did we add any new variables with these equations? Yep. So we have a new force vector F34. So we have 9 equations and 2, 4, 6, 8, 10, 11, 12 variables. Any questions about that one? And then the last member we have to isolate is member 4. Okay, so up at the top, that's joint E. What loads are applied to member 4? Yeah, there's only a force on 4 by 2. And that 5,000 is applied to member 2, so that one doesn't show up here. So we have F42, which is negative F24. And then at the midpoint, at D, what loads are applied to member 4? Yep, so there's the force on 4 by 3, and we already have 3, 4, so I'll call that negative F34. And then the last one is down at the roller. What loads are applied to member 4 at the roller? So, yeah, we already have the RC. The way to do that, so these are all force vectors, unknown force vectors, all the ones with the double subscripts. And so for those, when we go from one contact force to the other one, we just take the negative and switch the subscripts. That force RC is a scalar variable. That's a force with a known direction. So the way that we deal with that is we keep the same variable, we still call it RC, and we just change the direction of the arrow. So now it's pointing this way, but we still call it RC. If you, this is, people do this a lot. You think like, well, if changing the arrow is good, I'm going to go for the deluxe model and change the arrow and make that negative, to make it extra clear. And I know like when you do that, it's clear to you, at least at the time that you did it, it's clear what you're doing. But what that really means, if you have an arrow and then a negative thing associated with it, says take a unit vector in this direction and multiply it by a negative number, which actually is the same thing as a positive number times a vector in the other direction. Okay, so if you did an arrow like this and called that negative RC, you'd really be talking about the exact opposite of what you mean. Okay, fourth moment. I'll put the about point at the top. So for the force, negative F24, the row vector is 0. Force vector is negative F24x, negative F24y. And the cross product is 0. And then the force, negative F34. This whole thing has a length of 1. So the row vector from the about point to the middle of this beam is 0, negative 5. Force vector is negative F34x, negative F34y. And so you get 0 minus 0.5 F34x. And then the last one is this RC. The row vector is 0, negative 1. The force vector is in the positive y direction, so 0, positive RC. And the cross product 0. But you know it has to be because you're allowed to move this force anywhere along its line of action. And that means you can move it right to the about point. Okay, so Newton's second law says negative F24x, negative F24y, plus negative F34x, negative F34y, plus 0 RC is equal to zeros. And the moment equation says basically that F34x is equal to 0. Negative 0.5 F34x is equal to 0. So equation 10 says negative F24x minus F34x is equal to 0. 11 says negative F24y minus F34y plus RC is equal to 0. And equation 12 says negative 0.5 F34x is equal to 0. So now we have 12 equations. At the end of isolating body 3, we had 12 variables. Did we add any new variables in this one? No. So we have 12 variables still. And that means we can solve this. So now, let's not fill this out, but do something like this. And what you get okay, so you get that F12 is equal to 4330, 4330. F13 is equal to 0, 0. That's weird. F24 is 0, 6830. F34 is 0. The force vector RA is negative 4330, positive 2500. That scalar variable RC is 6830. And then the reaction moment at the wall is 1830. We did all this in SI units, so all the forces are newtons. And the moment is Newton meters. Now I'm going to take one more step, and I'm going to go from these variable values that we found to redrawing each one of those individual members with all of its external forces shown on it. So first, member 1, and you can think this through again, or you can just go back to the free body diagrams you already did. So here's member 1. All we have to do is put in the values that we just found. So on the left end is F12 and F13. And since those are acting at the same place, you can add those two together. Well, F13 is 0 vector. So over here you just have 4330, 4330. And then at the middle from the roller, you have a downward force with a value of 6830. And then at the wall, you have the force vector RA. So negative 4330, positive 2500. And you have the couple 1830. And if we'd gotten a negative value for MR, you have two choices about how to represent that. You can draw it like this and write negative 1830, or you can draw the moment going the other direction and call it positive 1830. Okay, now member 2. So from before, we know that member 2 has negative F12 acting by itself down at the left end point. And then at the right end point, there's F24 and that 5,000 Newton force. So this is negative 4330, negative 4330. To 4 is 06830. Then that downward force of 5,000 is positive 4330, negative 2500. Since those two are acting at the same point, you can represent this, just add those two together. And it's 4330, 4330. Then member 3, that's the other diagonal one. Left end we have negative F13, and at the right end we have F34. F13, this is the one that was zeros, so that's nothing. And then up here we have the force on 4 by 3. I guess that's also zeros. And then member 4, that's the vertical member. Up at the top we have the force, we have negative force on 2 by 4. negative F24. So that's 0, negative 6830. And then negative F34 is 0. And then down here we have an upward force of 6830. And you know, a lot of times the reason that you want to do an analysis of the loads happening in a structure is you're trying to figure out, you know, where you're concerned about this thing breaking, or like, you know, where the deformation is going to be big in the parts of. So in order to do that, you first figure out the external loads on these members, and then you go in and calculate internal loads and stresses and things like that. We haven't talked about that stuff yet, but in order to go into more detail about what's happening inside these pieces, you need to first figure out, if you isolate that piece, what are the loads on it? Okay. Yeah, right. That is definitely true. Which is a little strange looking, isn't it? But I'm pretty sure these numbers are right, though. But yeah, exactly. I mean, if you were trying to design this thing and you thought like, okay, I need this to support it, and then you did the calculation and this has no force on it, then maybe you could take it out. One thing that you have to think about always is like, okay, so if it's perfectly in this position without that piece, it means that it would be in static equilibrium. But you also have to think about the stability of it, you know? And so, yeah, so because there's error in all of these measurements and all, you know, these values we're using. So what if this was like half a degree this way, or that was 5002 or something, you know, and you didn't have member 3 there? Would it still stay in static equilibrium? It sort of looks like it doesn't. I think it's probably, that's just probably sort of dumb luck of the forces I chose, you know. But yeah, you could definitely, what you could very reasonably say is like, you know, this force, this member, we need to be strong. You know, that's where the big loads are. This one, that could just be like a thin cable or something. That's not providing very much. Well, no, this says it wouldn't. But if you have, so what you're thinking of is sort of, it's a real thing. If you have a body, so all of the things we do calculations of in this class are called statically determinate. That means that just based on statics, you can figure out what the forces are. You don't need any more information about it. But if you have structures that are statically indeterminate, like for example, if I put, so this is in static equilibrium like this, right? What if I took another member and connected this to here? You know, obviously that would make it stronger. But if you did the static calculation with that fifth piece in there, the equations would tell you that you can't solve it anymore. There's no unique solution for that, because there are loads that could be taken up by member 2, say, and they could also be taken up by this new member, you know? Yeah, well, there are ways to calculate that, but it depends on the deformation properties of the materials you're using. So then you would say, okay, well, if this is copper and this is steel, I know some things about the deformation, and I can use that to figure out how much of the force is held by this, how much by the other thing. But not necessarily. Yeah, so those calculations can get a little complicated, but that's the idea. If something is statically determinate, like everything we're doing in this class, then what the calculations tell you it is, that's what it is, as long as it's in that position. One thing I want to point out, have I talked about two force bodies at all? I haven't mentioned that, have I? Okay. So if you have a body that is only loaded by forces at two different locations, so those are what we're going to call two force bodies. Yep. That's right. So all these structures problems, that's all we're trying to do. So if you have a body that's loaded by force vectors in only two locations, then there's two things that have to happen. Those two force vectors have to be equal and opposite. So those two force vectors number one have to be equal and opposite. And number two, they have to act along the line between the two forces, or between the two locations. Oh, and one thing, this is important. I didn't say it in words. You know, in this class, everything we're dealing with is in equilibrium. There's no accelerations. This isn't true in general. You know, like obviously, well, think of like a baseball that's being hit. When someone hits a baseball, there are two forces acting on the ball: gravity and the force the bat's applying to it. Those aren't equal and opposite. The thing is that ball's just accelerating a lot. So this stuff is only true when you're in static equilibrium, like we always are in this class. So if a body is loaded by force vectors in only two locations and it's in static equilibrium, and the force vectors have to be equal and opposite, and they have to act along the line between where those forces are. You can make intuitive sense out of this. So let's think of this as the body. So first, what if the forces aren't equal and opposite? What if you have one force like this and another force like this? Yeah, then it's going to accelerate. You add up those two vectors, you get a non-zero net force, and so that thing's accelerating. And so one has to hold, or this thing is going to have a translational acceleration of the center of mass. So now think about, okay, we know they have to be equal and opposite. What if they're not acting along the line between those two locations? So say those are equal and opposite. Could that be in static equilibrium? What would that member do? It would spin, yeah, exactly. So This first requirement says that it doesn't accelerate. The second one says it doesn't have angular acceleration. So there are two possibilities. There are only two forces acting on it. It can be in tension or compression. And those requirements are what the truss simplification is based on, and I'll talk about that next time a little bit. We're not going to spend a lot of time on that. But let's look back at this example, see how that came up. Okay, so member 1, that has 3 force vectors and a couple acting on it. So that's not a 2-force member. We don't, based on these requirements, we don't know anything about the directions of those forces. Member 2, this one, even though we originally had these written as 2 different forces, they're acting at the same location, and so it's really just a single force vector. So this body only has 2 force vectors acting on it, one up here and the one here. And what you see if you look at those force vectors is they're equal and opposite. You see the components there. This thing's at 45 degrees, so if you look at the, you could use inverse tangent or something to figure out that direction. And what you'd see is that this one is pulling on the member that way, and this one's pulling on the member that way. So if a 2-force member is in static equilibrium, it can only be in pure tension or pure compression. This one's in pure tension. Member 3 is the one that doesn't do anything. Member 4, well, we had originally 3 force vectors applied to it, but it turned out one was 0. So this one only has 2 non-zero force vectors acting on it. The one at the top is downward, 6830. The one at the bottom is upward, 6830. So this member is in compression. Any questions about that? So you might think there must be a way to, sort of take advantage of that fact. Like if you have a 2-force member, you could assume that, remember, we have fewer variables if we're representing a member, or if we're representing a force with a known direction, right? If we know the direction, that's only a single variable. If we don't know the magnitude or the direction, that's 2 variables, right? So you might think, okay, well, if there's a 2-force member, maybe I can represent that as a force with a known direction and cut down the number of variables that I'm using. You might not think that. You might not even be listening right now. But if you did think that, you would be correct. So that's the idea of the truss simplification, is that if you have a body, a structure that's made out of nothing but 2 force members, then each one of those, the forces in each one of those bodies can be represented with a single variable, instead of isolating those bodies and coming up with 3 equations and all these variables for each one. And it just simplifies things a lot. The problem is, in order to use that simplification, a body each body can only have 2 forces acting on it. And if those 2 forces are the connections between the member you're isolating and the surrounding things, that leaves out gravity as something you can put in. So any structure that has weight for the individual members, you can't treat as you can't use this truss simplification. And obviously that's a big hole in this simplified approach, Any questions? You can because, well, I don't, people used to use it in real life to do calculations for certain things. Because like if you have a bridge, okay, that is made out of I-beams or whatever, and then on top of these I-beams is a whole bunch of concrete and then all this traffic going over it or whatever. The external forces applied by the concrete and the traffic going over it is so much higher than the weights of those I-beams that you get a pretty good approximation even by leaving it out, even though the I-beams are obviously pretty heavy. It's dwarfed by the other forces that are applied. And so that's the idea. If the weight of the individual members is small compared to the other forces, then you can get a pretty good approximation. But I don't know this. I don't know like when people design bridges and structures that are, that are in the like traditional like truss, that you would have done calculations using this truss simplification before. All of this stuff is like computerized now, so I assume they don't leave out anything. They just put everything in, and if it doesn't end up affecting the problem that much, like who cares? The computer did it just as fast. But in the old days, if you had a bridge that was made up of, 200, a huge number of members, and there was no easy way to just plug your results into a program to get numbers out of it. Someone was going to have to sit there and do those calculations. Cutting down the number of variables was important for keeping costs down for designing things. That's not really the case anymore. So it used to be that this truss simplification was a super useful thing for industry. Now it's just kind of an interesting fact. Because you can actually Google truss calculators and you can find one online that'll do those calculations for you. There's not really any need anymore to be able to do that by hand. But any other questions? Well, no, but I'm gonna talk about it because so the only reason that you have to know it is okay. So you will never in your professional life have to do hand truss calculations. That I promise you. But it is possible that in future classes, somebody is going to give you a truss as the background to a problem and say, like, first you have to. And so I'm going to give you enough background that if you have to, you can go back to your notes and do it, But other than that, you don't need it for this class, and you'll only need it. If you ever need it again, you'll only need it for future classes a couple times. Okay, let's stop.